Hello, this is the third video of Game Theory Series 2 for OCR Discrete Further Mathematics. And we will look at how to solve the m times n game as a linear programming problem and then interpret the solution. In the previous video, we formulated a 3x3 zero-sum game as a linear programming problem. Here we have the objective function to maximise p equal to v, which stood for the value of the game for player A. We had identified decision variables p, q and r as the probabilities that player A would adopt strategies p, q or r respectively. And we had come up with the constraints by reading down the columns and then rearranging, so that we had v minus p plus 8q plus 6r, brackets, and then taken those brackets out to get the signs right, and set that less than or equal to 0 for each, so as inequalities. We also noted that because player A must play one of the strategies PQR, that gives us p plus q plus r is less than or equal to 1, and that those probabilities must be non-negative. Solving a linear programming problem using the simplex method is covered in the linear programming series videos. So here we will just read the solution. However, we need to notice that we've introduced the slack variables S, T, U and W to turn inequalities into equalities, ready to use the simplex method to solve. However, note that because we know that p plus q plus r equals 1, we are expecting W to turn out to be 0. So here we have the constraints put into an initial simplex tableau. Note that this top row is the objective function row. And then we can see, for example, that v minus p minus 8q minus 6r plus s is this one here, where we have v minus p minus 8q minus 6r plus s, and then the 0, and so on for the remaining 3 constraints. So we are not going to go through the iterations in this video, and indeed if you had an LP solver this could be used. But if we were to carry out several simplex iterations, we would get to this final tableau here. Note that once the objective row only contains positive elements, then a solution has been found. So what does the table tell us? You can see from the highlighted cells from the objective function, which is shown in this row, that we were trying to maximise p equal to v, and we can see that this has value 5. On the next line we can see that small p has a value of 3/7, that q has a value of 4/7, and that then the next row indicates that the v equals 5, which was what we were expecting from the objective function row. We will note that we also get from the last row a value for u equal to 11/7. We note that some of the variables do not appear. So for example r is not given a value, nor is s, nor t, nor w. So these are all equal to 0. To interpret the solutions more fully, we do need to remember that we added 5 to all the cells or values in the payoff matrix at the beginning. So we do now need to subtract 5 from that optimal P value. So where P was 5, now by subtracting 5, that takes us to the revised P being 0. Note that the probabilities, those P, Q, R, etc. do not change. So, if we use capital V for the adjusted value of V, in other words small v minus 5, then we still have that the probability P was 3/7, Q is 4/7, that R is 0, the slack variables ST and W is 0, but that the slack variable U would be 11/7. And this solution tells us that the optimum strategy for player A would be to play strategy P for 3/7 of the time, and strategy Q for 4/7 of the time, and strategy R not at all. And the value of the game, the expected minimum for player A, will be 0. And this means that both A and B neither win nor lose in the long term in this particular game, if A plays these optimal mixed strategies. To summarise solving m times n zero-sum games, first we would check for a stable solution. If there is a stable solution, we can use that pure play safe strategy. If there is no stable solution, we have to look for a mixed strategy. Initially, we would check for dominance arguments to see if we could reduce the size of the game, if at all possible, and make our lives simpler. If the game reduces to a 2 times n form, we can then solve it by sketching graphs. And if the game reduces to an m times 2 form, then we can solve this by transposing the matrix and sketching graphs. Both of these scenarios were dealt with in the last game theory series. If the game does not reduce, then it can't be solved graphically, as there are too many variables. And in this case, as we've seen in this video, we would formulate it as a linear programming problem and then use the simplex algorithm. Now, in reality, linear programming problems are solved using computer software, as they're rather time-consuming. In the next video, we consider the Nash equilibrium for zero-sum games.